Open Maps on your phone and just watch the blue dot for a second. It slides along the road and it knows which street you're on, and when you turn, it turns with you. Except, it doesn't actually know where you are at all, because the signal feeding that dot is genuinely bad. It's coming from satellites 12,000 miles up, broadcasting a timestamp, and your phone works out how far away each one is by measuring how long that message took to arrive at the speed of light, which means being off by a millionth of a second puts you off by 300 meters. On a clear day, with nothing overhead, a good receiver will get you within a few meters, which is fine. But walk between two buildings and the signal stops coming straight at you and starts bouncing. It arrives off glass and concrete, having taken the scenic route, and your phone has no way of knowing that, so it just believes it. And in the city, the error on a single satellite can be 30 meters or more. So, if you plotted the raw numbers your phone actually gets, you wouldn't get a smooth line at all. You'd get a scatter plot, a stagger of points all over the block, jumping 4 meters left, then 8 back, some of them inside buildings, one of them inside a river. Yet, the dot is smooth, which means your phone isn't showing you the GPS, and never was. It's showing you a guess. Something in there is taking that mess and quietly turning it into a clean line down the road, 60 times a second, and getting it right pretty much always. That something is about 65 years old, and was on board when the Apollo 11 came down onto the moon, and it sends fighter jets and self-driving cars, guiding how our navigation works in our everyday lives by being wrong every single time. So here's the actual algorithm. You've got two guesses about something, both of them are wrong, and you average them. And that's it, the whole algorithm. But averaging the guesses is the actual hardest part. Picture yourself walking down a long hallway, counting your steps, and you reckon you're about 10 meters in. Though you're not certain, because your stride isn't identical every time, and you might have lost count for a second. So call it 10, give or take about 2 meters. Then, your phone picks up a sensor around the corridor, which says you're at 14. So which one do you take? Well, not either of them on its own, because that's throwing away good information. But 12 also isn't the right answer. 12 is the true average, which is what you get by splitting the difference. But that assumes both guesses are equally trustworthy even when they aren't. Your step count is off by about 2 meters, whereas the wall sensor is cheap and it's bouncing a signal around the corridor, so it's off by about 4. So you lean into the one you trust more. You weigh each guess by how wrong it might be, you do the arithmetic, and you land on 10.8, which stands close to your own count, because your count is the better of the two, but still pulled a little way toward the sensor, because the sensor isn't worthless, it just knows less than you do. And weighing them this way handles the extreme on its own, without you ever having to add a rule for them. If the sensor were perfect, zero error, dead accurate, then the weighing would handle everything, and you jump straight to 14 and forget your own count, which is exactly right. And if it were garbage, off by maybe 100 meters, then the weighing would ignore it, and you'd stay more or less where you were. Same formula both times, but the error just goes away after taking the uncertainty seriously. 10.8. That is the Kalman filter. Everything else in this video is the same move done over and over and over again. But the filter does something strange that you might not notice on the first glance. Before the sensor said anything, you were unsure by about 2 meters, and the sensor was unsure by 4, and after you combine them, you're somehow off by 1.8. That's weird, because you had a shaky guess, you mixed in a worse guess, and you came out more certain than you started. Your best information going in was your own step count at 2 meters, and you finished higher than that by listening to something less reliable than yourself. The way to see that is to change what where I am even looks like in your head, because so far, we've been picturing numbers, and what I actually want you to imagine is a shape. Your 10 meters isn't a point, it's a hill, tall in the middle where you think you probably are and sloping down on both sides, and the width of that hill is your doubt. The more narrow, the more confident, and vice versa. And the sensor's value is a hill too, sitting further down the corridor and much wider than yours. So push the two hills together and ask where the real answer is, because it has to be somewhere where your hill and the sensor's hill agrees on, which means that anywhere only one of them likes, the other one rules out. 8 meters, you're fine with it, but the sensor says that that's too far back. Gone. 15, the sensor's perfectly happy, but you know for a fact you haven't walked that far. Gone. And what's left? The script they both agree is reasonable is narrower than either hill was on its own. That's the whole reason. Two vague opinions contradict each other, because they're vague in different directions, and the place where they overlap is tight, which points straight at a flaw of this algorithm, because if your 2 points happen to be wrong in the same way, with the same bias and the same blind spot, then they don't constrain each other at all. They agree, and the filter gets confident, even though it's confidently wrong. It's assuming your errors are independent, and even when they aren't, it'll happily lie to you with a very narrow hill. Because of course, you're not actually standing still in a hallway, and nothing worth tracking ever holds still, which is usually the entire reason you're tracking it in the first place. So the filter runs in a loop, and it only does two things. First, it guesses, which means taking what I knew a moment ago and pushing it forward in time, using whatever I understand about how the world works. You were at 10.8, you're walking about a meter per second. 1 second's gone by, so you're probably somewhere around 11.8 now. But look at what that guess cost you. Nobody measured anything, nothing new came in, and that was pure guesswork from an assumption. You assumed you kept walking at the same speed, and maybe you slowed down, or maybe you stopped to tie your shoe, so the hill gets wider. Every moment you go without checking reality, you get a little less sure of yourself, and the longer you coast, the vaguer you get, which is exactly how it should work. Then it checks, and a new reading arrives and gets weighed against the prediction in exactly the way we just did. 2 guesses weighed by exactly how much each one deserves, and the hill snaps back in tight. Widen, tighten, guess correct, 60 times a second, and that's the loop. That's your blue dot. Which means that, for the most time, between GPS readings, your phone is flatly making up, coasting you forward at whatever speed you were doing, and when the next reading finally lands, it doesn't jump to it. It just leans that way by however much the reading is earned. Which is why a wild GPS spike that should have thrown you into the river doesn't even wobble the dot, because the filter has already worked out that reading isn't worth much, so it barely moves. But you can get this wrong in both directions, and 2 failures look completely different. Tell the filter to trust its own predictions too much and it holds too firm, and the reality can be waving at it while it keeps gliding serenely down the road as it expected, ignoring measurement after measurement. Tell it to trust the sensors too much and it gets twitchy instead, chasing after every bit of noise, at which point there's basically no filter and you're back to the raw scatter. The whole idea of using one of these is landing somewhere sensible between stubborn and jumpy. And once you've got that loop running, something else you might not expect happens. Go back to the hallway and check something, because at no point did anything in that story measure your speed. Your step counter and the wall sensor both gave you a position, and every single number that came in was a position, but speed never came up once. And yet, the filter knows exactly how fast you're walking. Here's how that happens. When you told it to push the guess forward using the speed, you handed it a rule that ties the 2 things together. So from that point on, position and speed combine inside the filter. And once 2 things are joined like that, learning about one of them teaches you about the other. So watch it work. The filter predicts you'll be at 11.8. But the reading comes back saying 12.5, which means that you're ahead of where you thought it'd be. And there are only 2 ways to explain a gap like that. Either your position estimate was off, or you're walking a bit faster than the filter currently believes. It has no way of telling which, so it does a bit of both, nudging the position forward and nudging the speed estimate up. Then it happens again and again, and if you're generally walking faster than it thought, then the same arrow keeps turning up in the same direction, over and over, and the speed estimate keeps getting nudged the same way until it stops being wrong. A few hundred rounds of that, and the filter is holding on to an accurate number for your walking speed, which is a number that nobody ever gave it, one it worked out entirely out of the shape of its own mistakes. That's why when it turns up whenever the number you actually want is the one you can't measure. Point it at an aircraft and it gives you the win, which nothing on board measures directly, and point it at a battery and it tells you the charge left, even though there's no sensor in the world that reads charge. You get a voltage and current and temperature, and the number you actually want has to be worked out from how those 3 behave together. It pulls the hidden thing out of the visible one. Though not always, and it's worth knowing when, because the link generally has to be there. If you never tell the filter that position depends on speed, then it never learns anything about speed, ever. And if 2 hidden qualities happens to push the measurements around in the same way, then it can't separate them at all, so it reports some blend of the 2 and never untangle them, no matter how much data you throw at it. Engineers call that being unobservable, and no amount of clever filtering fixes it, because what you need is a different sensor. But when the link is there, it works, and that's exactly the problem NASA was sitting on. Rudolf Kalman published this in 1960, and it went bad, as his own field basically decided it wasn't right. He'd trained as an electrical engineer, but the electrical engineering journals wouldn't take the paper, so the math that would end up flying people to the moon was published in the journal Basic Engineering, which was a mechanical engineering journal. And it wasn't stupidity, because there's already a way to do this, and it was famous. Norbert Wiener had worked out a way to pull a signal out of noise back in the 40s, and his method was beautiful and rigorous, and the thing that everybody in the field had built a career on. It had just 2 problems, which were that it assumed that things were essentially stationary, and that it wanted an effectively infinite history of past data to work with. Kalman threw all of that out, and instead of frequency and infinite history, he tracked the state of the system, meaning where it is and how fast it's going, and updated that one measurement at a time, carrying nothing forward but a running summary. No archive and no assumption meant that tomorrow looks just like yesterday. It's easy to hear 1960 breakthrough and picture applause, but the people best equipped in the world to understand what he'd done looked at it and shrugged. What saved it was one conversation, because that same year, Kalman went out to NASA and talked to an engineer named Stanley Schmidt, who happened to be stuck on a problem. Working out where their spacecraft is, on the way to the moon, in real time, from sensors that lie on a computer that barely exists yet. Schmidt didn't have 20 years invested in the old way. He had a deadline. So he heard it and got it immediately, and within months, his group had it running in simulation for the flight around the moon, which left exactly one problem: the computer itself. The Apollo guidance computer had 4 kilobytes of RAM to work with. A single photo off your phone is hundreds of times bigger than that, and this was the machine that had to fly people to space and bring them back home again. It also couldn't handle decimals properly because it ran 15-bit fixed-point arithmetic, which means that every number had a hard limit on how precise it could be, and anything finer than that, and the limit simply chopped it off. That sounds fine until you remember what the filter is actually carrying around, because the filter isn't only tracking where you are, it's also tracking how short it is, the hill, and the width of it. And it updates that the width thousands of times, each update built on top of the last one. So the tiny rounding errors compound, and the number representing your uncertainty starts drifting, because there's nothing in the arithmetic stopping it. So they rebuilt it. Schmidt cut the computation down to something the machine could actually carry, a version called a Schmidt-Kalman filter. And then a graduate student at MIT named James Potter worked out something better. Don't store the uncertainty itself. Store a kind of square root of it, and then reconstruct the real thing whenever you need it, because the square root multiplied by itself cannot come out negative. He made the bad outcome impossible, rather than unlikely, and now that's called square root filtering, and 60 years later is still what you reach for when you don't trust your hardware. Then the program was woven, and I mean that literally, because the finished software was threaded hand by hand through tiny magnetic rings, a wire passing through a ring for 1, and then on the outside for 0. And once it was woven, it couldn't be changed. If there was a bug in it, the bug was an actual object. That's what was running when the lunar module came down. And it never stopped running. It's in the plane you fly on, holding one position together out of GPS and gyroscopes, none of which agree with each other. Weather models use it, with the whole atmosphere as the thing being tracked. And the coolest part about it is that it shows you are never going to get a clean measurement of anything, ever. Every number you will ever have is wrong by some amount. You can't quite pin down. The filter's answer is stranger than that, because what it says is to stop treating your guess as a number and start treating it as a number plus how much you bet on it, and then carry that doubt around with you as its own real quantity, and update it just as carefully as you update the answer. 65 years later, and nobody's come up with a better idea than that. Make sure to like and subscribe, and check out my other videos. Peace out.